All right, so good afternoon. My name is Chris Elsner with Office of Undergraduate Research. I provide a support role for the Undergraduate Research Committee, which is a collection of faculty and staff from across campus with the goal of expanding, enhancing, and promoting undergraduate research opportunities across U of A. And so we are piloting these faculty lunch and learn sessions. This is our second one of the semester to try to provide some additional resources for faculty members to think about research opportunities, how they can better incorporate research in their courses or curriculum, or how to make more meaningful research experiences that they're already offering to undergraduate students. And so this committee is the primary sponsor of the events and helps us promote and talk about these things. And all of the presenters today are part of that committee. And so additional support also comes from the Office of Undergraduate Research and the College of Science, who's the benefactor for your lunches today. So please enjoy those. We will be, like I said, recording this meeting on Zoom. So your colleagues and peers can access it at a later time. With that being said, you can kind of see the frame that will be here included for the recording. But we also want to make sure all of the dialogue is captured on microphones. And so with a smaller crowd, we can probably be a little bit more informal in terms of Q&A during the presentations. But if you do have a question during the presentation, I'll have an additional microphone or two that I can bring around if you need to ask questions. So please just kind of, give me the hi sign or something and I'll run over and get you a microphone. And so with that, I want to introduce our first speaker for today. Dr. Molly Bolger is an associate professor in molecular and cellular biology. Her research focuses on curricular design and student learning in biology. So the recent projects have included designing introductory biology laboratory curriculum and investigating how authentic model-based inquiry within curriculum supports student scientific agency and skills. And both Molly and Deirdre will be presenting under the auspices of the Curr Transformations Project. So this is a grant from the Council on Undergraduate Research, who has a grant recipient from the National Science Foundation, focusing on transforming the curriculum in STEM education across the nation in terms of building research into early stage academic courses rather than the more apprentice-based model. And so that is what both MCB and CBC are exploring and what Molly and Deirdre will be talking a little bit more about today. And then our last presenters, Jeff and Katie, will be talking about some examples of how they've been able to incorporate citizen science and data science to incorporate these things into the classroom. And so with that, I'll turn it over to Molly to go ahead and get us started for today. Thank you, Molly.
Try to time myself. Thanks, everyone, for being here at this end of the semester. I'm curious, we just have a few folks. Maybe you could just say what department you're from, because do we need that on? I don't know if we need that on audio. Figuring out how many of us are biologists or other kinds, I'm a biologist, but other kinds of scientists or who everyone is. Maybe just shout out like what department you're from. Okay. Okay. Entomology, math. Your chemistry. Yeah, and office of, I'm sorry. German studies. Okay, great. So we've got some diversity here. That's good. Okay, so I will be talking today about a project we've been doing for a couple years. Introductory level students in a laboratory course. And I like to get started just giving an example of something that a student did. And this is in this laboratory course. Sorry, I'm learning how to use this pointer here. They draw models, and we'll talk a little bit more about that in a moment. This is an example of a model that a student came up with from data that they were doing in the lab, and this is like a cartoon model trying to explain. And so they really had to come up with their own ideas here. And so they were interviewed about this as well as kind of their own confidence in science. And so I thought I would share a quote from that interview with you. So the interviewer asked, students must come up with their own hypothesis models, or scientists must come up with their own hypothesis models experiments. Do you feel like you've gained confidence in doing this over the course of the semester? And the student, this is the student's response. So Oh yeah, probably a lot, actually. Before, I kind of liked the answer given to me. I was more of like the type of person where, just be back here for the video, where I know that if I know the answer, then cool, I can probably figure things out from there. Whereas here in this lab, basically, we have to figure things out in the beginning, the middle, and the end, and that really helped me a lot. I think it's easier now to come up with hypotheses. And so they were actually able to reflect on the fact that, you know, science is not just about someone giving you the answers. That's kind of the main point of a lot of what I'm going to talk about today. And so backing up to the big picture in biology, we had this document come out quite a few years ago now called Vision and Change in Undergraduate Biology. And I really like this quote from this document. So, given the accelerating pace and complexity of modern science, students who are steeped in content without understanding how that knowledge is generated and how or even whether it should be used and applied will be at a disadvantage in thinking about science in the future. So I think we would probably all agree with that. And this is, of course, not just in biology. Skills are really what everyone's wanting us to prepare students to do. So, you know, critical and creative thinking, problem solving, gathering relevant information, thinking about parts of a system and how they interact, how are people able to communicate, all of these skills that we really want our students to be prepared with. So hopefully we all agree to that. So with that, kind of my overarching goal for my work is how do we create learning environments that support and motivate students with a diverse set of backgrounds, right? We have students at this campus, and particularly in the class I work in, who come with lots of different coursework background, lots of different levels of preparedness. We want to support all of these students in their science learning, as well as, I think, push things to the next level to help integrate the skills that they should be learning with the content that they're learning. So that's the overarching goal. How do we specifically get there? In my group, we think a lot about models. And so models mean lots of things to different people. And when I use the word model, I'm usually just talking about these 2D drawings that scientists make to think about the phenomena that they're investigating. So in our papers in biology, there's often like a model like this at the end of a paper, and intermixed with all of the data. And so what I'm really interested in is how do we get students at this interface between models and data, because that's where a lot of the thinking of science occurs. Specifically, we try to engage students in a modeling or in parts of a modeling cycle. So if you think about, as a scientist, if we have some model that we may have, that would allow us to come up with a testable hypothesis or some sort of prediction that we could then plan an experiment around. We would conduct that experiment and gather some data. And then that might help us then evaluate our model and whether or not the model needs to change or stay the same. And so maybe we would revise the model. And so what I like to think about is how can we place students at different parts of this modeling cycle in order to make what they're doing in class more authentic. And so I will mention the two curriculum designs that we've done along these lines. And we recently, well, this one's recent, this is not so recently published on. If you want to read the details of this, feel free to take a look at these papers. TRIM, I won't talk about today, I'm just going to mention it now, is a large lecture course for upper division students where we have students working on data interpretation with provided models. So we're really putting them at that last part of the modeling cycle in a lecture course, a content course, working on that skill. The thing I will talk about today is kind of in keeping with the rest of the talks. We're going to talk about AIM Bio that we came up with, which is authentic inquiry through modeling in biology. And this is really cool because it's a lab class and we can actually engage students in the whole cycle of modeling. So this is a picture of students in a lab class, probably not at the U of A because our labs do not look this beautiful, but they look like they're doing science, right? I mean, this is kind of, the lab is the place where students can really do science, and it's kind of exciting. but they may or may not really be doing the cognitive work of doing science. So if you think about maybe what often happens in a lab class or a traditional lab class, you have some concept that you may be studying about in class or something that motivates performing some experiment that generates evidence, and that evidence confirms the concept. So you're kind of just in this cycle. That's not really how science is done, right? We all know this. And so what we're trying to do in our course, and what we've done so far, is focus on helping students build explanations. So by contrast, what they're doing here is we're providing them with a phenomenon that they can observe, which will motivate some sort of model or explanation of that phenomena, which can lead to a test that they come up with, evidence that they gather, and that's going to help them revise their model. And so you could just go through this cycle as many times as you have time to, just like we do in science, to improve the explanation or the model based on the evidence that you have. And so where are we doing this? Obviously, we're doing this here at the U of A. We also had an instructor at Pima Community College where we tested out some of these things. Our ultimate goal is to reach the large number of students that we have enrolled in intro bio here every year and have a curriculum like this for that. So far, we've tested this out about 7 times in different sections, and we're getting ready to think about scaling up as kind of the next goal. This is an intro, as I said, bio lab course, and the things that we're doing, we try to base them on authentic research. So either published papers, often I'm going and embedding myself in my colleagues' labs down the hall, and we're learning about yeast, and then we're trying to carry some of that over into the lab. And so they're going through these cycles of inquiry and model revision. I think it's important to say that different from course-based undergraduate research experiences, which some of you guys may have heard a lot about, we're not aiming for our students to be creating data that could be published or publishable. It's more of an inquiry based on authentic research. Okay, let's see how we're doing on time. So, what are some of the principles that we use to design this? So, these are actually really hard and incredibly important for, I think, the success that we had. And we got these, most of these we didn't come up with ourselves. There's a whole literature on model-based inquiry, mostly in K-12 education. Not all, there's some in chemistry and physics and other places. We drew from that to come up with what are the principles that we should use to guide this work. And so one of them was that we wanted to have this is really more coming from the fact that we have diverse students in their preparation. We wanted to have multiple entry points for students with diverse preparation. So we wanted the task to be open enough that someone who had never taken a science class could still have productive ideas and get something out of it, but someone who might be a senior and physio major, and has taken several lab classes could actually start at a higher place and end at a higher place, so they could also get something out of it. Importantly, we centered on models as thinking tools. So this is a place where we tried to help students learn that the things that they were drawing, the models that they were creating, was a place for them to think about biology and as a tool just as it would be for us as a scientist. Probably the most challenging and most important design principle was this one, that we had to have phenomena for which there were multiple plausible models. Because if there's one right answer that's easy, it kind of ruins the whole thing, because then everyone's just trying to get to the right answer. And also, I didn't put it up here, but along with that, we didn't focus on canonical models. And so if they left not knowing the exact answer to the problem that we gave, that's fine. It's not going to hurt them in future classes, because the point was that they were getting towards more plausible things, right? And that they were able to focus on evidence and how that supported it. So along with that, we focused on the relationship between data that they were collecting and the models that they were making. And we did a lot of work to make a scientific classroom community. So this was not a competitive environment. Students were encouraged to share ideas with each other. In fact, because as you'll see, they were doing very different experiments. Often other people's experiments could help inform the model that they would have at the end. And so we talk a lot about diversity of ideas being a good thing. And we also use, I would recommend anyone Benchling. We finally figured that out. It's a software I can tell you later, but makes sharing of like data and things like that among students easy. So yes. She said you're using scenarios.
When you're trying to come up with something that has multiple plausible models, but you're basing it on papers where presumably they got to a conclusion at the end of the paper, how are you just choosing figure one and then asking them to sort of figure out where the scientists could go from there? Is that
well, I mean, so when I say it's based on published things, so if you the other course I've talked about, the upper division course, it is more like literally based on figures from papers, and in that case, like, we would give some figures and there would only be one model. But in this case, we're more like we're reading the literature, and it may be about a phenomenon that was like one of them in here is how yeast mate and shmoo and stuff like that. So there may be like years of literature on that, and we're just using that to inform what we do. So we're not giving them like a piece of data and saying, come in model from that. So it's something where I think maybe it'll be clear when I give you an example where students will just tend to come up on their own different explanations for it. And I'll show you one that I think hopefully will make that a little more. Yeah. Okay, great question. Actually, it's right here. This is the first one. And so this is a unit where we were focusing on bacteria growth. And I know not everyone in here is a biologist, but most of our students are not either. So I think you can probably have some ideas about this. So what's happening here is we're looking at gram-positive and gram-negative bacteria. So students learn how to do a gram stain. So they're looking under the microscope at bacteria. And we call them species A and species E. And what they observe is that in a media called number 1 here, that is a rich media that kind of grows everything. You see species A and species E can each individually grow, or if you put them both, they can also both reproduce and grow together. We also have a media number 2 that is kind of a sparer media. So there are fewer things to help things grow in there. And it includes this polymer called colaminic acid in there. And so what you notice here is that species A can grow just fine. Species E does not grow. But when you mix both a little bit of species A and species E in this media, they will both grow up. And so we pose this as a puzzle kind of to students. They observe it, and then they will come up with their own models. So maybe I'll give you 30 seconds. Think about your own model for this before I show you. It's more fun if you do this. Usually I would have you write it in a group, but we already have 20 minutes. But you can imagine, how would you explain this, right? And what kind of processes are you having to use to come up with an explanation for this? Okay, so we did that, our students. And then we got some different kinds of hypotheses. And really cool thing is that these categories of models are pretty stable. So you get like 3 or 4 of the same, similar different ones repeatably, but it's never everyone does the same. So one of the ones we got was something like this, where they think that the acid is actually attacking species E and that A is somehow protecting species E. And so like a hypothesis would go something like this. If colaminic acid, and they then had tools and came up with a hypothesis, well, if we added colaminic acid to medium 1, species E's success would be diminished. Also, if we removed it from medium 2, then they would have greater success. So they kind of thought of the acid as this problematic thing for species E. And then the next week, they get to do their own experiments about this, and they came up with, I'm not showing you all the controls, this is just a simplified version, but basically they added acid to medium number 1, and they took it away from medium number 2. And in fact, they show that their hypothesis is wrong, but that's not the point at this point, that they have their own idea and they're testing it. Another group said something like, they drew a picture you can kind of see here, where one species is giving something off to the other species that might help it grow. And they actually drew it as a question mark. They don't know what that something is, but they think there must be something. So that's one of the things we try to encourage, like generating, even if you're not sure what that something is, like you can put it in your model. And so this was their hypothesis. E cannot survive in mutant number 2 without mutant A because it releases something that E can use. A consumes columinic acid and E consumes the byproduct. And so with their tests, one of their tests was they actually took media that had bacteria A growing in it. They spun it out and took the supernatant, and so then they saw that species E could actually grow in the media that previously had species A in it. So this is an experiment they did, which actually gives a positive result. And I won't show you more examples at this point. There are other kinds of these similar things. This is a cool example of, this is an initial and a final model of a unit. So this is a group who had some ideas that got much more visualized molecularly at the end of the unit, and also kind of articulated. What's really cool here is they actually have an idea, and this is very close to what actually happens, that columinic acid that species A can actually have a receptor for that, which causes it to change its gene expression to secrete an enzyme that then breaks down columinic acid so that E can use the columinic acid monomers, which is close to what happens. But they figured that out through their experiments and other people's experiments. So, keeping a close, yeah, I'm getting pretty low on time. So, I won't go through this, but this is an outline of the curriculum that we've created. There's a lot of different model organisms, different topics, and I'd be happy to share that with people who are interested later. I will briefly, in my 1 minute remaining, tell you the answers to the research that we're doing on this, that we've done on this, that we just published. So we looked at 3 things. To what extent does this curriculum help students actually take ownership and agency over themselves as scientists and their ability to do this? They learn things about the nature of science and what about skills. And so kind of, maybe I'll only have time to show you the first one. I think it's the most exciting in a way. We asked them just like, have you ever felt like a scientist? We didn't even say like in this class or something like that. And here's the results that we got from the unrevised versus our AIM Bio students. And so we got a lot more people saying yes and specifying our lab compared to the control or the unrevised section. A lot of people said yes and they didn't specify biolab at all. And then more people were saying, no, I've never felt like that in the unrevised section. And this is a typical kind of response when we asked them to explain. There was a lot of different ones, but timer. Okay, yeah. Turn this silly thing off. I feel like a scientist when I can come to my own conclusion based on experiments I can see the results from, and things like of that nature were common responses that we saw. We also, I just wanted to read this. I think it's loaded. I'll give you a moment to read this response from an interview of a student. So, I mean, they kind of see that they're doing something that's very different than what they've done in the past. And quantitative analysis-wise, we did this project ownership survey, which was designed to compare cures or course-based undergraduate research experiences to traditional labs, and we got similar results. Specifically that students in the AIM Bio curriculum had a significantly better, lower is better in this case, score on their project ownership compared to unrevised. And we also saw that at community college, which was really cool. I won't show you the data, but we have them and you can read about them. That they also learned about what it is to do science. So their ability to think about what an experiment is and things like that improved and became more sophisticated efficiency. So if we can measure it, as well as their skills for generally reasoning about things. So with that, I will take maybe one or two questions before we go to the next talk. Okay.
How did you decide on which students would be in the revised section? Was it a random?
It was
Registry?
random. Yeah, I mean, we have tons of sections, right? And so we just took over one or two or three, depending on the semester, because we wanted it to be, this could be for students with any interest. And we kept things fair in terms of we weren't asking more from them or anything that they would feel unfairly treated. Yeah.
Did you prevent students from looking up your compounds on Google? There's
We-
something that you prohibited in terms of not allowing them
No,
to.
we did not. And it's a good question. We did not prohibit. And I will say, I mean, I think it's a combination of, we did sometimes hide things and make them Googleable, like we didn't tell them what species A was. Although most of the time Google wouldn't have gotten it. I mean, they would have had to be in like papers from 1980 and like, you know, like everywhere. It took us forever to figure out this stuff. It wasn't, these are not like canonical models you can just Google and there it is. Also, we disincentivize that totally. So like, lab reports were not great. There was really no incentive to, other than you want to figure this out, for like getting the right answer. And so it was all about different answers. You have to be able to justify why your experiment fits with your model. Was really right. Right. Now that's not to say that we didn't tell them, like we had quizzes about content that was indirectly related to the model. We give them feedback when we were walking around about their ideas. So it's not like we didn't care that they learned biology. We just didn't incentivize them to get the specific answer. I think I see you had, and then you had it, and then you, yeah, okay.
Yeah, this is more of a comment. I find it extremely interesting because I wanted to challenge myself as a non-scientist to see how far we would have something in common. I would say that if I just adapt slightly the vocabulary, not much, we do exactly the same thing in the humanities. With one proviso, I think our data, our sort of subject matter is much more complicated than yours because much more because we're dealing with people, literature, poetry, art,
Absolutely.
and it's much more difficult to come up with concrete data. But we do exactly the same thing in the humanities. And I'm very happy that I feel like we have the same language here. We want to do the same thing with our students. We give them a model. We want them to experiment. We want them to explore. Teamwork, all that is sort of kind of the cycle, except we have many more loopholes and
Yeah.
escape routes than you do. But it's wonderful.
Well, my response to that is, number one, when I think about my big goal here, it's I want students to know that they can think, right? That know that they're able to come up with their own ideas and that that's valuable and they should be able to evaluate them. That crosses all disciplines. And also as someone who does research in the social sciences at this point, all my research is in education. People are very complex. Yeah.
So two sort of, I think, related questions. One is, what did you grade on, given, you know, that can either help or interfere with their participation
Given what?
epistemically?
I'm sorry.
Either help or interfere with their epistemic participation in the projects. And secondly, how, and I imagine related, I assume they were working in groups, or did they all get to design experiments individually? And if they did work in groups, how did you manage the dynamics associated with that?
Two very good questions, and both big parts of our iterative design of trying to make it better each time. The grading, the things we had were weekly. This kind of structure came from the existing lab. We had weekly quizzes in class, almost every week, in class and online, which were content-based. So we gave them readings about simple dogma or something like that. So there was content that we were kind of giving them just in time to help them with their background. And so they did get grades for that. They got grades for turning in all of the worksheets and scaffolds and things and just putting forth effort. And we gave feedback on those, but not usually points graded for right, wrong. And then the kind of where they got the most feedback on their process was on the 4 lab reports that they turned in this semester. And we had a rubric, and it was really, we kind of gave a lot of comments, especially in the beginning, and we saw a lot of improvement in their writing and things, but the points were not, you didn't figure out the end. I mean, as I said before, it was about like, okay, here's your model, but I don't understand your explanation, or here's your model and you explained it, but you didn't really connect specific pieces of data that you had. Or I think you may not have drawn the right conclusion. And so some points would be taken off for those things to help them learn those skills, and lots of feedback. Second question, grouping. Yes, they were in groups, and groups of 3 that they kept throughout the semester. And in fact, for the bacteria one, which is the first time they designed their own experiments, we actually paired 2 groups that had a similar model after the first week to come up with an experiment together so that we could manage only having 4 different experiments at that point. But then in later units where they had a little more confidence and ability, we were able to manage having like, 8 different experiments happening in the same room. But yeah, they didn't get to come up, but they, you know, they negotiated it. It's really interesting how they negotiated as a team, like, what do we want to test? And sometimes they tested 2 things because they had different ideas. Yeah.
I've been doing a similar sort of thing where I give the students kind of vague directions and they have to have more specific responses. But one of the things I've noticed is that the students sort of segregate out. There's a few leaders and a few stragglers and a whole lot of followers. And I'm just wondering, do you see that same sort of
Not as
motivation?
much as I thought it. I mean, of course, there are people who are more dominant than others, but I'm not sure. I think that, well, first off, there is individual accountability strategically at different places. So the lab reports are their own, and that's pretty strictly enforced. And sometimes they have to turn things in individually, even though they worked on it as a team. So there's some accountability for that. Also, I think we have had a lot of examples of anecdotally of students who were really coming in extraordinarily naive, like I could give examples, but I won't right now, but like extraordinarily naive. And they do struggle in the beginning, but I think because it is so open and there's a lot of encouragement of, you know, it's okay to have your ideas, those people actually take off. And so I think there's something about the openness of it that can engage those students who might otherwise just get left behind. And I don't know what exactly the number of variables are, but even at the community college, my instructor said, she said, this is the first, she teaches traditional labs. And she said, and now I have people who like were totally disengaged and were the straggling behind. And they're like, this is my idea. This, you know, they took ownership of it. So yeah, I mean, I'm sure there's people who are more and less engaged, but it doesn't seem to be the struggling students who necessarily are. I don't know if that answers, but yeah. Any other questions, comments? Thank you.
All right, well, please join me in thanking Dr. Bolger for her presentation. Next up is Dr. Deirdre Belle-Oudry. Deirdre is a Director of Academic Services and a Senior Lecturer in Chemistry. She teaches Instrumental Analysis Lab and Chemical Safety course. She has been in the department for 15 years, and most of that time managing teaching laboratories. All right, so please join me in welcoming Deirdre.
Thank you. Okay. So I was going to talk about what the Kerr transformation that's been going on in the chemistry and biochemistry department. There's a whole team of us that are involved in this. Most of us are laboratory managers, but we are also guided by a faculty member, Vicente Talencare, who's actually an expert in chemical education. So we're really fortunate to have him kind of guide our conversations through this process. So what we've been trying to do is more or less align goals and practices throughout the curriculum, particularly the laboratory curriculum. When we first started the career transformation, well, actually, let's start before that. So for many years, we've been working on transforming many of our undergraduate labs to be more like guided inquiry projects rather than cookbook type activities. And so this has been going on at many levels. First year chemistry, we usually refer to as general chemistry. So in that class, we have thousands of students because we are a service course for many different majors in the university. So we'll have, 3,000, 4,000 students taking general chemistry in any given semester. In that curriculum, for many years now, they've been running what's called a chemical thinking program. And in that program, the laboratory activities are organized by projects. And so they're group projects, and the students, it's more of a guided inquiry type experience where students have to make decisions, and direct procedures are not spelled out for them. At higher levels, so organic chemistry is usually what people take in their second year. We do have, for the chemistry majors, there's a specific class that they take. So organic has a majors program, and in that laboratory, they have a final project. It's called Design Your Own Synthesis, and so they have to design a plan and carry out a synthesis of a new compound. But usually it's something that they found from the literature, and then they're doing their own version of it. In the analytical lab, that's usually a junior level lab, there's a final project as well. And in that one is more focused on forensic science. And so we give them some materials and say, this is some crime scenario, and this is the evidence that we gathered from it. And those students then have to do some kind of chemical analysis with the plan that they developed to prove who the suspect was that committed this crime. So we've been kind of going that way for a while in many different classes. And then most of the efforts though have been uncoordinated. So we're all kind of doing our own thing. There are different lab managers for most of these labs. We communicate, but not on a regular or formal basis. And so it was good to kind of come together for this career transformation and find out what each of us is doing and try and coordinate it a little better. So, so initially when we got the career grant, we decided that we were going to focus on analyzing what we have existing, and then design some new lab activities. And so initially we were focusing on general chemistry second semester. Whoops, sorry about that. I keep hitting the wrong button. Second semester general chemistry. And so we were looking at that and saying, well, what can we do in there that's really a research type experience? And so we were almost reinventing the wheel and saying, we were going to pilot a couple of sections of general chemistry lab and just kind of give students a project that was really research focused. It was actually really challenging because with so many different things going on, so many different sections of this class, having one section that was completely different was going to be difficult for our prep room and for our teaching assistants and such. So we were a little bit overwhelmed by it, I guess, at first. And we were also looking at our organic chemistry non-majors class and having one or two sections of that was going to be more of a research focused type experience. And so, we spent a few months kind of meeting every week and trying to figure out what projects we were going to use in these classes. And then, lo and behold, we had the first visit of our career consultants. So they came to the department and they went through our undergrad labs and looked at what we were doing, particularly the general chemistry classes that were really the project focused experiences they were already doing. And they were actually really impressed with what was going on in there. However, they did say that what we need to do is, rather than coming up with new research experiences, is to align and integrate the activities that we're doing at all the different levels in our curriculum, because it's already there, we just haven't integrated it together. So that was nice to hear. So it's a little less overwhelming to do that than to come up with new ideas for research projects. So yes. Oh my. Okay. Okay, so so what we're doing now is trying to define and align the learning outcomes across our whole lab curriculum. So we're really trying to have a progression throughout the curriculum so that students learn step by step and become more independent researchers as they go through. So we're looking at what we're doing in all of our lab courses. We're meeting every week and we're discussing and coming up with strategies to make this a more integrated experience in our majors curriculum. And so we're having a lot of conversations about that. So we have to do this in the context of our department and program goals. And so a couple of years ago, we developed, when I say we, I mean our undergraduate program committee developed a set of learning goals for the chemistry majors. This had to be done. You guys probably know that we have to do assessment for our programs. And so one of the first things you do is come up with a set of learning outcomes. So this was done in the UPC, Undergrad Program Committee. And we developed a set of goals for chem majors, what we expect them to be able to do when they finish with their degree. And so we wanted to make sure that we kept these in mind when we were doing our career transformation, because we still need to have majors that can do these things when they graduate. So with those in mind, then we started doing this project-based framework. So we have at all different levels in the curriculum a project. So starting with the freshman chemistry class, design your own paint is one project that they do that the students find really memorable and useful. We get a lot of good feedback on that. Creating a soap product, so they make their own soap and they do that and learn the chemistry behind that. We're working on, at the sophomore level, a couple of new projects. Design your own scent. There's another one that they're doing for that. So design your own scent is the non-majors project that's being developed. Design your own synthesis is for the majors class. So at the sophomore level, we have one for non-majors and majors. The junior level lab, as I mentioned, there's a forensic project. And in the senior level, one instance of a project in the senior level, there's a few senior classes, but one that's required and that I think is kind of like a capstone experience for our students is this materials characterization project. So it's a pretty open-ended project where they have to design their own analysis of a sample. I run off to Target and I shop for samples that have really complex and interesting things in them, and then give the students the sample, be dog food or shampoo or anything like that, and tell them to find out how much vitamin E, for example, is in the shampoo. Give them a whole list of questions, and they work on that as a team and design their own plan for that and carry it out. So our laboratory work in these classes is becoming more focused on investigating phenomenon rather than just being told what to do and confirming some answer that is already known. Okay, so this is just an example from our general chemistry class where they're given a challenge and given a few lab periods, and they work as a group. It's usually a group of 4, I believe, 3 or 4. And just to show you, that's kind of open-ended. We give them some videos to watch or some, it's infographics to look at. And then they have to kind of use what they learned from those videos and apply it to a new situation. So it is more a research type experience. But as a group, what we've been doing is meeting every week and trying to come up with our plan. So this is what we call our scaffolding matrix for so different scientific practices that are related to research. So for example, applying qualitative or quantitative analysis to interpret data. So that's one thing that students should be able to do. It's a research skill. So the skills that are involved in that, you know, we've kind of developed different skill sets that address each of these different practices. And then we're looking at in the different levels of our curriculum. So from foundational classes like general chemistry to more intermediate classes like analytical chemistry, and then to the upper level senior classes, how these skills are being developed, gradually increasing in complexity as they go through the curriculum. So that's why we call it a scaffold, because as they move up, they're expected to do more and more. So this looks really, you know, it's just one table, but this has taken us months to develop, because we're having conversations about, well, what is it that you expect your students to be able to do at this level? And it's actually really good soul searching experience and really good conversations that come out of it. So we're almost done with it. I think it's due next week to the CUR group, so we have to finish it soon. But this is where we are right now in developing the scaffold. So, and then we're learning, you know, we're working on defining scientific practices. And this is an example from general chemistry of, you know, how we're kind of scaffolding even within a class itself, you know, what's expected of students as they go through the course and increasing in complexity. So, so there's scaffolding both within each course as well as within, you know, across the curriculum. Yeah, so this mapping is really helping us to create the alignment that I think the CUR consultants were kind of pushing us to get to. Okay, so this is an example of one aspect that we are working on. So in terms of scaffolding, so one of the skills that we expect our students to have when they leave is to be able to communicate, you know, in writing or in oral communication. But we kind of, couple of weeks, we focused on technical communication. And this was an eye-opening experience, because some of us who teach upper level courses thought students should know how to write a lab report when they get here. But nobody's really taught them that per se. So this was an idea that we came up with for teaching them how to write. I think the next slide shows it a little more. It's a little bigger and you can kind of see. So we developed this document that we're going to implement in general chemistry and organic chemistry, so sophomore and freshman levels. And what it is it's a worksheet. So instead of them writing a lab report, they go to this worksheet and they're asked to tell us what are the central claims? What are you claiming is happening here? Describe the evidence that you see for this phenomenon that you're investigating, and then arguments that connect the evidence to the claim that you're making. So you make some hypothesis, here's the evidence, now say why that evidence proves your hypothesis or not. And this is kind of helping them build up to being able to write a lab report later on in upper levels, because we're showing them these different things that we're asking you to tell us. This is kind of corresponding to the results and discussion portion of a lab report or a scientific paper that you might write later on as you go up in the curriculum. Let me just go back because I'm going to show you where we're going from there. So that's the freshman sophomore level document that will help them then build up to the junior and senior level document, which in the past, we've always just said, you always have to write a lab report for every experiment you do. Well, re-looking at that, because in reality, not every student that graduates from our program is going out and becoming a faculty member or doing research for their career. Many of them will get jobs where instead of writing a full lab report, they might do what's called a technical communication, which is a more abbreviated version of a lab report. So, you know, you need certain aspects of a lab report, but you don't need everything to be a lab report. So this new format for, you know, some of the writing that the students do, it will help, I think it will help them connect what they learned in sophomore to, you know, what they need to present to us in the junior level class. And then as they get to the senior level, they might do some of these, but then they'll start writing the more formal lab reports as well. So we're kind of stepping up from, you know, a worksheet where we kind of guide them to what the different sections of the lab report will be. And then eventually they'll have to connect that to, you know, ramp it up as they go up through the curriculum to a formal writing style. So, you know, this is helping them build arguments and being able to present those results in a written format. So we are going to implement that in next spring, this spring coming up, in chemistry 151 and 243A labs. So we'll see how that works out, if this helps students really understand how to write and what things are important to include in these. Okay, so we're also implementing some new revised project guides in Chem 151 this spring. We're implementing some new projects in Chem 243, which is the organic chemistry, in the spring as well. So we've been kind of working hard at coming up with some new ideas for projects that are research focused. And we're going to kind of encourage students to build arguments and being able to communicate their arguments by having some dedicated time within these 2 lab courses, within the lab period, to share and discuss results and kind of debate what they found. So that's where we are now. We're still continuing to meet every week and kind of continue developing our scaffolding for different research skills. But that's, you know, just kind of in a nutshell what we've been working on. So I'd be happy to answer any questions about that.
I just wanted to, you didn't seem to be aware of this, so I thought I would tell you. For us, the worksheet consists of a JAX template for a manuscript submission. And we give them that and we say, here's, and what's been very helpful is I have them send me their docx version. We mark it up using track changes, send it back to them. And then when they're finally ready to submit, they submit a PDF. And it seems to be very helpful for those that are willing to take advantage of it. We still have a number of students that won't send me an intermediate document, though. They will only send me the PDF at the end. And I don't really understand why you wouldn't want to let somebody mark up your paper before you turn it in.
Yeah, really.
And the other thing we haven't done, I think, is to get upper division writing credit for this, because I think they deserve it for what they're doing. So
what Dr. Polt is referring to is he teaches the upper level organic synthesis lab. It's many students take it, but it's not a required lab. It's an elective lab. Right. It's another capstone experience. So, and I'm hoping that this scaffolding document will help them get to the point where they can fill in that template more accurately, more appropriately. Because, yeah, in our senior lab, we also, in instrumental analysis, we just expect them to write a formal lab report. And, you know, it's kind of, we tell them what should be in it, but I think unless they've had some practice at knowing, you know, how to make a claim, how to support the claim and that kind of thing, it's hard to get to that point. Yeah.
I really like the idea of the scaffolds, and they seem really like you could map out everything that you're sort of doing within a class and within a curriculum. I'm wondering if you ever show students themselves the scaffolds. as a way for them to know what their trajectory is and whether that would be a useful thing, or if you think it would be not useful?
Well, this is really in the development stage. I have no problem. We're not trying to hide it from them, and I think that we do want that writing document. We want to show them how that translates into, from this. That's why we put on the side of the document is, whoops. Oh, I can get there. On the side of the document is, what are the corresponding, in an actual journal, paper, or lab report, what would be the corresponding sections that would correspond to these, making the claim that would and giving the background information would be the introduction, and then, making your arguments and giving your evidence, that would be results and discussion. So we don't have a problem, and we actually want to do that and show them how that translates to. Any other questions, Molly?
Yes, I have two questions, if that's okay, if there's time. But one was, I also like this idea of scaffolding, because these are the very skills that students struggle with and need feedback on. I wonder though, because our students, I guess selfishly, come over and take the freshman and sophomore level classes, they probably might not make it into your majors courses. I mean, would it be possible to consider at least once, and after you've done the scaffold, at least once in the semester, practicing actually writing it out a little bit more to get that writing skill more and more, because they won't all become our majors. And I just wonder if you'd like to.
Yeah, I guess I hadn't thought about that. I guess, once people finish sophomore organic, if they're not majors, they don't know how to write a lab report, right? Because they've only seen this worksheet. I don't know how many of the I guess we'd have to look at the population of the students and where they go. Are you expecting them to write lab reports in Bio 181?
Well, yeah, we do that, but I mean, and they learn, but I suspect this writing skill is we all know it's a big one, right? And so, I mean, I think probably all majors would like as much writing practice as we can manage to create, and they can manage to write, in those early years. But just throwing them in there, like you said, is not. So I like the idea of scaffolding. It should get a little practice.
Yeah, I guess we've been focusing more on our own majors selfishly, but yeah, because sophomore level for us is actually Chem 247, which they do kind of go a little beyond this in there. They will write a lab report on their final project, and so it is a little further along. But yeah, we hadn't really thought about, whether the other people in that sophomore class need to write lab reports for some other discipline.
My other question, if we have time, was I really thought it was cool how you were bringing everyone together that teaches classes and thinking trajectory-wise about those. And I was just curious if there's anything that kind of surprising or interesting that came out of those meetings about when you looked at all the classes, kind of the lab classes together. Or what those conversations are like.
I think my first surprise was realizing that they weren't writing lab reports before they got to my class. But so that was the first eye-opening experience. And I actually was really surprised at how much of the Gen Chem program is doing this project work, where it's very open-ended. And the students do have to kind of design their own things. I was surprised at how much independence they're given there. Thank you.
All right, well, please join me in thanking Dr. Belle-Oudry for her presentation. All All right. So next up are going to be Dr. Jeffrey Oliver and Dr. Kathleen Prudick. Dr. Oliver is a data science specialist at the University Libraries, supporting data literacy across campus. He provides data science training to students and researchers in order for them to effectively capitalize on the big data revolution. Dr. Prudick is a faculty member in the Department of Entomology with research interests in big data and conservation rather. She runs a citizen science web platform, eButterfly, which gathers data from butterfly enthusiasts to understand how climate change is impacting butterfly survival and distributions. Did we lose you? There we go. Okay, so this one's still on.
Hello? Yeah, we're good. All right, so we're going to tag team this. So you're going to see a lot of like exchanging of the microphones, and hopefully I won't drop it, but I'm not making any promises. Really? You don't trust me? That's fair. That's fair. Oh, wow. We just got so many. It's like double fist. But then no. All right. All right. Thanks everybody for coming. It's great to see the diversity of folks here, and especially at the end of the semester when we're all ready to crawl under a rock and never grade again. Today we're going to be talking about a module that Jeff and I developed in collaboration with a colleague at a small liberal arts institution. So this is a primarily undergraduate institution. We'll talk more about the details here. But really what we're going to be focusing on today is thinking about how the world has changed dramatically in the last 10 years in relation to data, and how we need to integrate those competencies into our classroom, often with faculty who are learning those new competencies on the fly. And how do we collaborate and help each other to do that in meaningful ways for the students? Okay, so I was just staring at my phone the other day. I was in jury duty and I was deprived from my phone for a whole day and almost freaked out. But just thinking about how much data that phone is producing every day, how much retailers know about those shoes that you've been looking at. Yeah, I got some head nods there. Yeah, mine are following me around. They're these really cute clogs. Anyways, so thinking about all this data that really exceeds the tools we've been using in the past. So Excel is not going to cut it anymore, folks, to be able to look at data and visualize it and come up with hypotheses. So it's a great time to be in the database business, right? And there's a lot of interest in data engineers and data scientists. But one of the issues we have is that I was in the elevator today, and every discipline seems to be struggling with finding the right people to help analyze that data. So how can we get our students in our disciplines to have those skills, to be able to take large amounts of data, to visualize it, to come up with hypotheses, test those hypotheses, and then communicate that information to make data-informed decisions? Okay, your turn.
This is my question to you all.
You going to say the question, or are you just
That's
gonna sit
what is data science? That's my question.
This is supposed to be in.
So we have applied statistics. This is good. So when you throw a question out to your class and they all stare at you with blank stares, that's what we're getting. If you ask 2 data scientists for a definition of data science, you'll get 3 different answers. So anybody else? Applied statistics. What else? So you've got the big data aspect of data science. That's good. Let's try for one more answer, maybe from this side of the room. You got more people. So drawing information or knowledge from large sets of data, often messy data that you did not collect, those sorts of things. So if, as I said, there's lots of different definitions for data science, but one of the more common formal definitions is data science is the intersection of applications and techniques from mathematics and statistics combined with computer science to apply to domain questions. And domain questions are areas like business, biology, astronomy, chemistry. So it really is a multidisciplinary intersectional endeavor. That's one part of the title of our talk. And the other kind of science that we talked about was,
which is where I come in, citizen science. So this is democratizing mostly data collection at this point. But we're getting to the point where we can democratize other parts of the data, the information production pipeline. Certainly in biodiversity, which is the area I work in, there's a lot of these web platforms, phone applications where thousands, if not millions of data points are collected annually about where critters and plants are and when they're there and who they're with. Okay, and so what you're capitalizing on is this recreational tendency for people to like to go out and discover and explore and engage in the natural world. And
you didn't even give them a chance to answer the question.
Oh, were they supposed to answer the question? Did I not get there? Our timing is not good today. We're still. Okay, so that's what citizen science is in my mind and what we use to approach here. And then you're up, right? No, okay. So we're talking about knowledge of local environments, knowledge gained through experience, submission of scientific data by large numbers of online volunteers. Okay, so that's how we're defining citizen science. Citizen science in this case is not outreach. It is more about data collection, data validation, QA, QC, those sort of things. Am I going with Wendy? I'm in charge of Wendy. So Wendy was our collaborator at the College of New Jersey. Wendy, she was a colleague when we were postdocs at Yale. The College of New Jersey is a small liberal arts institution. It's a institution out east, and she is by training a botanist. So she studies plants. And one of the courses she was teaching, she called me up and she goes, Katie, I'm teaching this plant insect class, but I'd really like them to learn about citizen science data and how to use it in a conservation or ecological sort of context. Great, that sounds great, Wendy. She goes, and I said, I will gladly help you with that. And she goes, wonderful. And then we talked to Jeff. And the three of us sat down and we talked about her class. And her class is really an upper division course. So we're talking juniors, seniors, about 20, 25 students in her class. They are all located in Ewing, New Jersey. So we had to think about how to do this remotely and asynchronously, but sometimes synchronously, which we'll get to. In this case, we had 24 students with access to a computer, okay? They had zero experience on with any sort of statistical software. They had zero experience with programming. Okay, so those are the parameters that Wendy set up for us. And she has some experience with R, and which is a programming language, and some experience with the development environment for that. Okay, go ahead. Oh, sorry, that's right. So we created this lesson prompt. And now in the lesson prompt, we were like, how will climate change? So we're, again, focusing it on the domain component of this, which is an ecology class. How will the climate change affect the distribution of butterflies? Because butterflies really are the best insect, honest. And their larval hosts across the continent over time. Now, one of the reasons we're able to do this is butterflies have a tremendous amount of citizen science data. There's a lot of recreational butterfly watchers. I don't know if you guys are familiar with bird watchers. They are also a highly motivated group of citizen scientists. Butterfly people aren't quite that crazy, but we're close. And so we've got these databases, these online open source databases that we can draw from. We can also draw from our knowledge about the plants they interact with. So this has been studied, well studied for over 200 years, and we know who likes to eat whom, as it turns out. So we're able to then ask the students to generate range maps for butterfly and their host relationships, and come up with hypotheses of what they think those range maps should look like. Okay? And eventually we're going to ask them to do some modeling to predict what's going to happen under different climate change scenarios. So what do you think? They have to come up with hypotheses about what they think the plants and the critters are going to do in 50 to 100 years. Okay. All right, so one of the first objectives we had was to combine, look at current distributions of bugs and their host plants. We actually gave them a little bit of a controlled garden, so we came up with a list of bugs that had adequate amount of data, and then we able to show them which plants went to that. So they had to go and search for those plants in the database, but they didn't have to make the connection of which exact plant that is. So that was sort of one of the informations that we gave them. We gave them, Jeff's going to talk a little bit how they generated these maps, but what they really had to do in this, the learning objective here was to think about, okay, these two groups interact in parasitic way. What do we think? How do we think that those ranges will overlap? Can butterflies occur in places without their plants? Can plants occur in places without their butterflies? And then thinking forward on what might limit where they can live. How will climate change impact those distributions? So we had 4 different components of this. So this was basically a module within the course. There were 4 different classes that the students had to do for the whole activity. The first one was an introduction to the citizen science platform we were using. This is a phone app, actually. If anybody wants to use it, they can. SciNaturalist. It's common in national parks, actually uses this a lot for their bioinventory, if anybody's looked at that. They are a very simple, straightforward app, and all of their data is then downloadable online. So they have a nice API, you get all that data off. And so they learned about citizen science data, how it's collected on this web application or web platform, how it's vetted, all of the QA/QC, and then where it's pushed to, which is the Global Bioinformatics Facility. So they learned about that data pipeline. They also learned about species distribution modeling. How do you make a species distribution model? What sort of assumptions are you making? What's the history behind distribution modeling? And what we're going to do here in this activity. Class 2 was an introduction to R, and the programming language to analyze the data, to generate these models and these of the species. Class 3 was using R to model future distributions. So in this one, they came up with hypotheses of what they thought the plants and the bugs would do, and then they tested those hypotheses by using these predictive models. And then in class 4, they took everything they did and they made a presentation that they gave to their class, fellow classmates. Now each group, I think it was, Wendy went with 3 or 4 people in a group, I don't remember, I think that's right. Each group had decided on what their species pair was, so they were working collaboratively on all these products. The grading was done so that each person though had to turn in their own independent maps, their synthesis of those maps, but then they did a collaborative group project at the end.
So the cool thing about this project is that all of these analyses could all be done in the programming language R. And so question, before this talk, how many folks here had heard of the programming language R? Raise your hand. Cool. And how many folks here use the programming language R? Cool. Excellent. So R is a programming language, and if you open up an R prompt, it looks like this, which is terrifying. What do I do?
everything.
There's nothing to do. So, so this is what you see when you open up an R prompt. And this is not something that we would want to inflict upon undergraduates who have no programming experience.
Faculty members either, let's be honest.
The R code necessary to run these analyses, that's no less daunting. So this is actually only a part of the code you need to run this analysis. So I also would not ask an undergraduate student with no programming experience, go do that thing without any guidance. And so what we did is I actually developed all the R scripts, but then did it in a guided practice framework. And this is very similar to what Dee just presented with the scaffolding for the technical communication, is that they did not have to write a script from scratch. As a matter of fact, they had to take a template that we provided and change it just a little bit. There were only 2 lines of code that they had to change. So you can see in the top left corner, there's 2 lines of code where they had to change where the data were coming from, and then also to change what to basically call the data that they spit out. I sort of diminutized the work that they had to do here, just changing 2 lines. I used the J word, just, which you don't want to do, but even those 2 lines provided ample potential for mistakes. I mean, learning opportunities where not putting quotation marks in, not understanding file paths, the difference between a dash and an underscore. These are all things that are critical, but for a novice, they may not know that. But because we had an instructor, Wendy, who actually knew the R language and R syntax, she was able to actually help them out, but also by letting them make these mistakes, we're providing a learning process and empowering them to actually feel like, oh my gosh, I actually just coded. So that was a very rewarding part of the experience. So when we actually came to do this, Katie and I are here in Tucson, but this class is happening on the East Coast. Through the wonders of technology, we were actually able to be live chat, just a text chat with Wendy when she was running all of these classes, which meant that Wendy is looking at one selection, one species of butterfly that the students wanted to analyze, and thought, well, I don't know what this butterfly eats, but we just happen to have a butterfly expert online here, so she could query Katie and say, hey, what should we use for this plant for these students? And then also, and this is something that we couldn't have done maybe 5 years ago, is that students would run the code and hit an error. And sometimes it was the PBKAC, so problem exists between keyboard and chair. Those happen. Those errors are frequent. I make them all the time. But sometimes it's a bug. I wrote this code, and I didn't write it right the first time. So the students found those errors. They weren't real happy when they saw error messages pop up, but Wendy could send me the error message in real time. I could look at it, update the code, send that new version to GitHub, and the students could download it immediately. And so as opposed to emailing back and forth over the couple weeks, downloading, compiling, recompiling, all that other business, we could actually get this done within a matter of minutes for the easy bugs. Some of the other bugs took a little while to work out. But that was one of the really cool things about this project that we could do. And some of the real learning outcomes I thought of this work was great.
Yeah, so we really focused on critical thinking, learning outcomes more than anything. There were some data literacy or data thinking outcomes that were in there in those different modules. But one of the things that the students in their feedback to us was they loved the idea about the developing hypotheses. So we gave them kind of a walled garden to play in, but they really had to dig in. They got to choose their bug, which they were very excited about. And I think Molly and Dee both talked about this. Did I get your name right? Okay, good. It's that point of the semester where I have no idea. I'm lucky I have pants on. Okay, good. But it was really the critical thinking that we were focusing on, and the students enjoyed that. So those hypotheses were central to this activity, I think, in terms of their engagement, in terms of their ownership, in terms of being able to provide a coding environment that they could feel successful in and feel like they made progress. We spent a lot of time also assessing data quality and trying to get at some of our own internal biases, specifically related to the word citizen science data. We talked about how they thought that that data would never be as good as that collected by professional scientists. And we talked a lot about why that was and what it was that they were seeing in museum collections, where a lot of this other data is, and where that data came from, often non-professionals, but we won't get into that. And so that understanding QA/QC, so quality assurance, quality control, and what that has in terms of implications of your analysis and interpretation. And one thing we did too with these critical thinkings is we made sure that they aligned with, in the College of Agriculture, we have what we call career competencies and critical thinking that's central in those. We wanted to make sure that we aligned with those career competencies that we have. So the knowledge, skills, and abilities, KSAs, associated with what critical thinking is. And we covered two of those. We would have, I think, liked to think about a third one, which is to make, so we covered forming a problem, evaluating the problem, but then making a recommendation on what a conservation plan could be using this data. We didn't have them do. So that might be a place where we could improve the lesson a little bit. So give them that extra piece of critical thinking, which is how do you make a data-informed decision with the information you generated? So as it turns out, we were able to make all of our data instructional products online, open source. So they are all on GitHub. Anybody can use them. That includes the slides, the lessons, the quizzes, the code, everything we have is all online and distributed in that way. We give a module approach, in which Jeff is going to explain in a second, so that people can sub in. Like if you wanted to work on fungus, you can work on fungus. You would have to change some of the code related to the names of the organisms, but the majority of the code is still there, right? So it's not limited to just plant-insect interaction. It could be across all biodiversity. And then these efforts ended up being published in Teaching Issues and Experiments in Ecology. And so that was another way we were able to disseminate what we were doing that other folks might find useful in their classroom.
So it was through that that publication in TIEE that somebody reached out, and as Katie alluded to, somebody works on a class in fungal plant diversity. So these are fungi which rely on plants for their existence, and he wanted to use the module in his class. And I thought, wow, that's really cool. Somebody's actually going to use this. Like, somebody read my paper. This is great. And so he wanted to do that. And of course, he did what you should do, which is he tested it out. And he found another bug. So he was testing it out, and he's like, this is great. I would love to use it, but I get an error, and I can't actually do this thing. And it was a bug that I thought I'd gotten a workaround, but clearly had not effectively made a workaround. So I dove into it again, and we fixed it, which is very cool. And just last week, he came back with the report, and it went really well in the class. I think part of it was a big part of why it was able to go off so well is that Wendy and Katie did a lot of work on providing the environment class. These are the sorts of things that you're going to want to cover. This is the kind of support that you're going to provide if you actually wanted to do this module. But through basically no communication with the people who developed the course, other than there's a bug, Peter was able to actually deploy this lesson in his own class. And which is something that I think is really cool, that we have this product then that can be used largely independent of us to really get at any kind of questions where you're dealing with biotic interaction. And that is all that we had prepared, but we'd be happy to take any questions. I'm going to turn my microphone over to Chris.
Oh, he's got one. You got one, yeah.
We got lots of mics. Questions?
So this is really great, and I am thinking about how to use this in my new class in the spring semester in a way. But one of the things I'm thinking about is using big data sets and analysis of big data sets as part of the honors section of my course. And I wonder if that you think that might not be enough time or exposure, that it's not the full class, but it's only a small fraction of the class that would be doing this kind of work. What are your thoughts?
I would go sort of say start small and do some refinements with your honors class. I think that one of the things that we really try to do is to make this accessible to a fairly novice audience. It requires time, it requires expertise and support, because we had all of the students go to the iNaturalist website and download the data, which requires an understanding of that interface and clicking on the right thing and searching for the right thing. So you have to provide that support, but like 24 undergraduate students with little background.
And no tears. Let's celebrate that.
We weren't there to see. We don't know that.
Wendy says no tears.
We actually had one R convert who hated R going into it and then was now actively using R.
Like did a special internship, like change their internship to be more R focused. Yeah, I think, starting for your sanity more than anything, because let's start with that first. The honors course seems like a great place to start. See what works for you and what doesn't. I will make a shameless plug. The library has someone who could help you. Good. Glad to hear that. Yeah, and we're both here on campus and happy to help with that. When I've worked with other honors sections in the past and for other things, and that I think that's a bite-sized piece to get going, and then maybe it is scalable for you depending on how many tiers happen. Yeah, no, nothing's naive.
I was just wondering why you did this with a class in New Jersey rather than UA students.
Wendy asked.
Okay.
So I don't teach a course at this point that is ecology. So I teach a history GE of all things. So I'm teaching a 160 about how insects have changed the course of human culture and civilizations in time. So not a lot of data science there yet, but that was kind of it. And Wendy asked, is that fair? Yeah.
Well, do you want to tell her about the pilot we're gonna?
Oh yeah, we can talk
launch
about
in
that. Yeah,
spring.
Kim's very excited. So Kim and Ramin, is that right? Were funded through the provost's office. Yes, and indirectly, yes, to broaden ASEMs, Arizona Science, Engineering, Math Scholars. Did I get that right? It's a good day. To expand it from the College of Science into the College of Agriculture, which is where I live. And what we're trying to do is think about that 1 to 2 unit experience that transfer students have, about making it that unit class to help orient them and create community, but then also give them a real data research experience. One of the things we're having trouble with, for I think 2 reasons, is getting undergraduates at scale into labs, right? So part of that is a lot of the tasks that they were doing previously have now been replaced by automation or, just not needed really in the research direction. And then another thing is, like, when you have that many of them, there's only so many faculty to go around. So that's how do we give them that meaningful experience that they can go and talk about in their first interview, their first fellowship, whatever. And so we're creating a class that has a component that's actually kind of fun. So Fiona McCarthy, and she's in animal comparative biomedical sciences. There we go. We're going to do, has anybody here heard of the game Humans versus Zombies? It's played all over the world on university campuses. It's a live action role-playing game of infectious disease. All that data is downloadable. So you can, and what it is students, you have a zombie zero who then goes and makes other zombies on campus. That's the idea. And it's tag. It's equivocally a tag game. But all that data is uploaded online, and then it's publicly available, so you can download it and analyze it. And so we're going to have the students download it and analyze it in a different context, this course, and try to give them some data literacy skills that then they can talk about when they apply for fellowships, internships, research experiences, during the summer. Hopefully it's scale. Is that what we're doing, Kim? Scale. That's what we're trying to do. Scale. We'll see how it goes. Molly.
So this kind of data analysis is obviously outside of my expertise, but I'm just trying to visualize. So like when the students do these modules, do they come up with completely like different things, or are there trends like that they would all come up with a similar trend? And would there be like limitless numbers of different things that different people could do? Or like, are there 5 or 6 things, you know, kind of what does it look like and how diverse is it? And
I think just like your lab, the same thing as your lab thing where you have to have options, right?
Mhm.
For more advanced students, you could probably make it limitless, right? And just let them sort of play in that big box. But to really set them up in the beginning, which is what we're talking foundational skills, we're probably going to, with the zombies course, we're definitely going to give them sort of a very confined play sandbox, walled garden to play in. And so they would, you know, run the code, but there might be a piece like we did here where they've got to substitute their own, and they're going to make mistakes when they substitute. It's going to happen. And they'll, again, that cooperative experience of learning what the mistakes are, communicating with each other. Oh my gosh, that's a hyphen, not an underscore. What were you thinking? Those kind of things. But yeah.
Well, you said you picked like 5 or 6 butterflies or something.
Yeah.
Like, but there could be more. Like, is there data available for more?
Yeah,
like
there's it's sort of like there's 700, 800 species of butterflies in the United States, and you know each butterfly probably has 30 host plants on average. So you know what I'm saying?
There's
Like
a lot of data.
there's a lot of variety there, and complexity that you can play with depending on how much you want to, what your learning objectives are.
And I think so. I was surprised at the diversity of hypotheses that the students came up with. I mean, I come in with my baggage and blind spots about the way the world works, and the students were they were applying all sorts of different aspects and things that they already learned in the class about plant and insect interactions to developing their hypotheses. And I think that while the data in and usually the data product at the end were pretty standard. Like, for example, for most forecast models, most organisms in North America are going to shift north. That's what happens. They shift north or they go upslope. And so we sort of knew that that was probably going to happen. And the question is like, then we could ask students, well, what are these other factors that could maybe, for all of the modeling that they did, they were using climate variables. So rainfall, temperature, things like that. But of course, it's not all water and rocks. There's other things on this planet. There are things like predators. There are things like other host plants. And all of the students actually, they did a good job of incorporating other aspects of those parts of biology into their hypotheses. So yeah.
I very much appreciated the space for students to make mistakes or learning opportunities. and I do think there's a bit of that needs to be lifted up in our teaching so that the students can gain the kind of skills we want them to have. Just from a student advising background even, or when I look at what we're reading about in terms of anxiety levels and the kinds of schooling experiences young people are having in middle school, high school, coming into college, it seems like they feel learning is sort of a zero-sum game. And I don't think that's what science needs. So I think some of what I see you all doing is really creating space for students to experiment and play, make mistakes and learn. And so thank you for the models that you've shared with us, because we'd like for more of that to happen on campus. And I think we help us retain students in the science disciplines on this campus.
I appreciate that. I think for me as a faculty member, my primary job is research. So the big change for me is when I figured out, oh, I can do evaluation in different places, right? And so I can let them play and make mistakes and learning opportunities, and you know, and that's great for them. They really enjoy it. And evaluation can be in a different way, in a different space. And it was like once I figured out the pipeline for that, then it was less anxiety on my end too, because we're trying to control my anxiety too, let's be honest.
Yeah, I would say shifting away from a focus on summative assessment, where it's just A's and B's, to more formative things that we can actually use the assessment tools themselves as learning techniques.
No, you're good. You're good. Yeah, Molly.
Amen, I guess. Like those are, I mean, yeah, absolutely. Like I think one of the things is figuring out, yeah, freeing yourself, as you're saying, of assessing like and critiquing for correctness every single thing, because that's no better way than to kill anyone's desire to come up with ideas, right? If they think that, but at the same time, that in some people's minds that translate, oh, it's just a free for all and there's no grades. No, that's not what it means. It means just kind of decoupling those things and thinking creatively about it. So it's great that you guys are thinking about that. That's all. Yeah.
Any last questions for Katie and Jeff, or for our earlier presenters, if you thought of anything after the fact?
So for those of you who'd like to learn more R, Jeff runs a R workshop weekly.
Yeah, Tuesday mornings in the science engineering library. They're on Tuesday morning. Science engineering.
And is that workshop for faculty or for students?
And you can work on.
Another workshop at Gentle Ben's on Thursdays with beer.
Yeah, so the Thursday afternoon hacky hour, 4 to 7 p.m. Gentle Ben's. They do have beer. I do not have beer. I do have coffee and usually homemade cookies. So a little plug there. If you're up on the health sciences campus, also Tuesday mornings there is a coffee and code section at the Catalyst Cafe and the new SRL. So there are more and more of the support systems for these communities of practice that we support faculty and students and postdoc and whoever needs help.
Also, I just wanted to mention that the U of A has an enhanced institutional membership with the Council for Undergraduate Research, Council on Undergraduate Research, CUR. And so on our UR site, ur.arizona.edu, if you go under resources, then you'll see a link for Council on Undergraduate Research. And then it has instructions there on how to sign up for your own membership under our institutional membership. So on the CUR page, once you are able to get your membership and log in, there's a tab for member resources. I'm saying this path so that it's documented for the recording. But on the CUR webpage, under member resources, you go to faculty and administrator resources, and then there's a bibliography catalogs. And then there's a link for integrating research into the curriculum bibliography. So there's a lot of resources there too, where you can look at other models and even see, I believe they have syllabi there too from different institutions.
All right, well, unless there are any other questions, please give a big round of applause for all of our presenters today. They're very gracious to volunteer their time and come to speak with us. So on the horizon, so the Office of Undergraduate Research provides a number of resources across campus. And so I'm more than happy to come out and talk with any student populations that you may serve and help them understand getting started in research. We have some resources for that on our website as well. But importantly, for students all across campus, not just in STEM, they can do research. And we really want to emphasize that and focus on that as well. So we have that workshop. I also offer a workshop for students called Research Communication Skills, and it doesn't necessarily go into in-depth about technical writing, but it helps them understand some of the basics of research communication and understanding their audience, thinking about how they're going to be presenting their work and what kind of format and the logistics with the different mediums they present in. And then I ask them to develop a little bit of an elevator pitch depending on kind of where they're at. If they're looking for research opportunities, the pitch is more about talking about their interests and communicating with faculty. If they've already done some research, then the elevator pitch is thinking about how do you present your work most often or more often than not in a poster session where you're communicating complex ideas in a very short amount of time over and over again to people from all different backgrounds. And so those are some of the workshops that we have available that I'm happy to come out out and present to your students. We offer these a number of times throughout the semester, and we'll have a bunch of them scheduled for National Undergraduate Research Week, which will be, I think, in the first or second week of April in the spring. And then we will also offer a couple more of these faculty lunch and learn sessions in the spring. One topic we're thinking about is asking Katie and Jeff to come back and really go more in depth about the citizen science. So we'll have a conversation with them and see if that's something that they're willing to do. And then we will also have another lunch and learn session as part of Undergraduate Research Week called a UR Symposium. And we're looking at bringing in some faculty members or some researchers who have really led this sector from outside U of A to come in and speak with faculty members and help us think about some of those things. So thank you very much for coming today. I hope you all enjoyed the workshop and got some good information out of it. Again, this will be posted online probably in the spring semester. So if you do have any colleagues or peers who you think would have benefited from this workshop, I'll be sure to send out the link and all the information where they can find it at a later date so you can share it with them. And good luck with the rest of your finals and courses. Thank you guys.